Good morning and thank you all for joining us for our webinar today as we take a look at electromagnetic design solutions. Today our webinar will be led by Roman Duplac, our Director of Advanced Simulation Solutions here at CAD Micro Solutions, Emmanuel Leroux, WW Industry Process Consultant Director, and Richard C. Ariel, Simulia Industry Process Consultant, both at Dassault Systems 3D Experience Works, Electromagnetics. Before I hand things over to Roman to kick us off, there are a couple of quick housekeeping items to mention. First, as usual, we'll save a few minutes at the end of today's session for a question and answer period. Feel free to type your questions into the GoToWebinar panel as they come up, and we'll do our best to get to them all at the end of today's webinar. The webinar will be recorded, and we'll be sending you the recording via email tomorrow. So if any questions do arise afterwards, you can feel free to respond to that email, and we'll be in touch shortly. We will be placing 2 questions for the audience in the chat during the webinar, so please keep an eye out for those. We do have a video in today's presentation, so if anyone experiences any issues with the audio volume, be sure to check your output, as if you are using headphones, the audio may come through your computer. All right, without further ado, I will pass things over to Roman to get us started.
Good morning and good afternoon, everyone. It's a pleasure to have you all participate and watch our webinar. Thank you very much for joining us. So as you know, our webinar right now that we're hosting is called Electromagnetic Design Solutions, focused on Simulia CST Studio Suite. Our agenda for this webinar includes the introduction of the current common technical and industrial challenges from an electromechanical standpoint. We're going to be focusing on basically 2 sections within this webinar. The first section will be presented by Emmanuel, focusing on antenna design and placement for Internet of Things, IoT, the application of the 5G sensors and network within an industrial plant, autonomous drive, where we're going to be focusing on examples of vehicle transportation, railway transportation mobility. We'll also do a deep dive on the industrial equipment industry and also wireless charging of battery smart devices. On the second section, which will be hosted by Richard, will be focused on PCB demo examples, which will include essentially import PCB board application. We'll also do signal integrity, power integrity, EMI and EMC analysis. And then once the section is done, we'll then have an open forum and a question and answer session, provided that the time is available. We are working towards for the webinar to be under 60 minutes, 1 hour. So as mentioned already by Madeline, our presenters are Emmanuel Leroux. He is with PhD, he is our Worldwide Industry Process Consultant Director for Dassault Systems 3D Experience. And then also Richard, he is our engineer in Simulia Industry Process Consultant for Dassault Systems 3D Experience. And as well as mentioned, my name is Roman Duplac. I'm the Director of Advanced Simulation Solutions for CAD Micro. Just to give you a quick background, who CAD Micro Solutions is, the company was started, it's a privately held company, which started in 1984, initially in the Toronto office, which is still currently our head office. And then we have 4 additional offices throughout Canada. One is in Montreal, another one is in Cambridge, which is an hour west of Toronto. And then on the far western part of Canada, Calgary, Alberta, and near Vancouver, New Westminster, BC. It is fully Canadian-owned company, and we're approaching a total of 70 employees. And we are a close partner in providing Dassault Systems SOLIDWORKS design solutions, as well as advanced simulation solutions. We also provide the innovative 3D printing solutions, various equipment that comes along with that, and the training, as well as VR and AR solutions, including 3D metrology equipment and scanning. So now I'd like to get into the industry trends and challenges that we're currently experiencing in the industry and how advanced simulation contributes to developing these technologies further. We're going to focus on carbon reducing green technologies, as we all are probably familiar with what's happening. And so the big push is developing technologies to reduce the carbon footprint. One of the ways that's going to be accomplished is by development and implementation of portable nuclear electric power generation stations. In addition to that is renewable energy turbines and solar panels, and also increasing the more energy dense battery storage systems. Further required is development of electric power transportation. Therefore, so that there's less carbon production. which therefore this requires individual electrical vehicles, electric power mass transit, which consists of trains basically, which is rail or ground vehicles such as buses. So all these need to be developed for electric power transportation, as well as electric aircraft. And to facilitate the charging of all these different types of vehicles, additional electric charging stations need to be installed. In order to further expedite and reduce the development time, it's critical to implement and use advanced simulation tools in your design engineering process. Going to the next slide, well, we also focus on other technologies that need to be developed for communication purposes and for safety improvement is 5G communication equipment, autonomous vehicle systems, as well as to basically optimize our manufacturing production systems, manufacturing optimization, where it includes Internet of Things, IoT, which falls in line with an Industry 4.0 initiative, as well as development of robotics and artificial intelligence and even blockchain technologies. Again, to further expedite the development of these technologies, it's critical to use advanced simulation tools. So that being said, that puts us into a position where we will start our first section very soon, and we'll pass on to Emmanuel. However, prior to Emmanuel starting his section, I wanted to bring to everyone's attention that we're going to be running a poll, and it's going to consist of a poll that there will be a question that will show up on the screen momentarily, as well as 2 questions that will be presented in the chat area. So I encourage you to please go ahead and read the questions and respond to those questions through the chat. Okay, very good. So all the poll results are in. Madeline, do you have do you have the results?
Yes, so 40% answered yes and 60% answered no.
Okay, very good. So that gives us an idea on how to continue on with our presentation by our presenters. So I think at this point, we will pass on the presentation to Emmanuel.
Hey everybody, good morning. So my part will be to give you some trends that are relevant for the electromagnetic simulation nowadays. And I took some hints about what is important for Canada in particular. So I made a deep dive and tried to propose some things that will be of your interest. We are going to make a travel on the mobile phone design, as it is a very good example of IoT. So basically, if you need to design a mobile phone today, it's quite challenging, especially because of the number of antennas that you need to design and place on the mobile phone. Think about 5G, for example. Everything is connected nowadays, not only mobile phone, but also smart devices, wearable devices, and also to pay. And the demand is very fast and demanding. So you need to integrate antennas. You need to take into account human exposure and co-site interferences between PCB and antenna. Here you have a deep dive on a mobile phone where you see the different kind of antennas you have on modern 5G phones. It's amazing, nothing to do with the simple spiral antenna you had in the years 2000. We try to have with 5G a direct path between the base station and the mobile phone. And this is not easy to be reached because of many obstacles. So you need to design what we call phased array, and you need to proper set amplitude and phase so that the beamforming of the array for the base station and for the mobile phone will fit together so that you obtain a good connection. You need fast communication, so you need a larger bandwidth. Let's have an example. Most of you did a speed test of your internet at home. Please compare what happened if you want to go to 5G. You see how much is the bandwidth. It's very high. And so you need proper design. Here we see an antenna. You see S parameter, where S parameter is minimum, means the radiation antenna is working. And you need to have really a good design of it. In fact, when you have a poor network, you are looking for network with your mobile phone, you don't find network, is because maybe the antenna is badly designed. Sometimes you need to introduce a matching network. This matching network will allow to reduce the coupling with the outer parts and hence also the duration of the battery. Here you see in green the improved design with a minimum of S11, which is the return loss at the right frequency that lead to perfect coverage. That means that you can proceed with your payment, for example. Other issue come to the fact that 5G antennas at those frequency have difficulty to pass through metals. So you can design several kind of covers for your mobile phone. And here we are going to make a comparison between a glass cover or plastic cover, and we are going to see what is the difference on the S parameter. We may also change the thickness of the cover to see the effect. At the end of the day, you come to optimization and an improved efficiency of 47%. Also, a good thing of 5G is that you should be able to communicate in omnidirectional way, in all directions. So that it could be that because of the effect of your finger, the radiation pattern will not be omnidirectional anymore. That means that it may be needed to insert several additional antennas on your mobile phone to complete this overall coverage, I would say. Very important is the specific absorbing rate that has to be calculated. This is something you find on the data sheet of your mobile phone when you purchase it. And here what we see, we can really optimize it. Further, here you see an optimization using an optimizer inside of the product, CST Studio Suite, that allow to optimize the radiation pattern to obtain a good coverage. Also, the success of your design will be to limit the coupling with the PCB. Here you see inside the mobile phone you have a PCB, and there is a USB channel. And as soon as there is a coupling between USB channel and mobile phone, you will have issues. So we can put some shields and have a reduced interferences of 22 dB here. At the end of the day, we come with a very good design, and it's a matter of work in a teamwork. So the antenna engineer, for example, he sees that the metal frame blocks the GSM antenna radiation, so it has to be changed. So he makes a notification to the structural engineer that will simulate the mobile phone again, and to make a drop test to see with the new shape, it still performs the requirements in terms of drop test. The antenna engineer is going to simulate again the new version that the mechanical engineer provided, and he realized that he obtained the perfect improved GSM antenna performance. So as a summary, we see that we could reach a better efficiency of the antenna by 47%, a lower, I would say, absorbing ratio, which is the power you have in your Yeoman head, by 35%. So it's very good result, and all this is achievable on the standalone product CST Studio Suite, but also on the ElectroMagnetic engineer role, which is a new role on the 3D experience platform on cloud. This is what I was showing earlier, that many people can collaborate on the cloud between electromagnetic engineer, mechanical engineer, durability, CFD, to work on the same product, having a unique source of truth on the 3D experience platform. Here now, I'm going to extrapolate a little bit the concept of the simulation for Internet of Things in the case of a smart factory. So imagine in your company, you have a plant, you have a factory, and you have several machines. And for 4.0 revolution, you need to drive those machines with sensors. So basically, you want to provide 5G coverage over all the space. And this can be done using our solution. And here you see 4 antennas where you have the red signal over here. You have 4 base stations that provide the 5G signal, okay? And because we have a possibility to simulate also with asymptotic solver using physical optic, we are able to take hypothesis we are in far field. We are quite far from the antenna, and we can really make a simulation without any mesh. We are not going to mesh the space. And we are able in short time to simulate a full coverage of 5G. And you can see here below, in red is where the field in volt per meter, electric field is very high. And in yellow, and in green even, it's too low. And you see leakage through the window over here. And you see near the docks there, the signal is not enough. It's not red, it's yellow. So what you can do, you can optimize the position of the 5G antenna. You can study if there is a coupling with some metallic piece nearby, so that you can really optimize the coverage of your 5G signal. which is a very good, I would say, extrapolation of the Internet of Things idea. Right, so now I change topic and I come back to what you said, Roman. In fact, I would say that electric mobility is becoming really an opportunity for the Earth and a challenge for the company. And so, if I want to see what we can simulate on a car, I would say that some years ago, people were interested to simulate the 77 gigahertz sensor radar that you have on the nose of the car, and then can be used really to predict the presence of a car in front of you and activate the brake when you need. This is the ACC feature that you can buy on your car. But more and more, what is the challenge is to design electrical motor. Most of them for the electric drive mobility are made using a permanent magnet synchronous machine that can be simulated very well with our solution. And we come to an efficiency map that can give you a good meet with your KPIs that you have starting from. Also, what is interesting is to simulate the presence of a human body inside of the car and see, for example, if you have a connection between the inverter, the battery, and the cable, if you can have, unfortunately, some induced current in your feet, for example, that should not be, and that is also dictated by a normative from bioelectromagnetism. Of course, we can simulate antenna placement and we can simulate wire harness. I'm going to come to that later on. Here we go. Now, still transportation and mobility, but we are talking about railways. And I heard that railways in Canada are using sometimes LRT system, which is a mixture of train and trams, especially in the suburbs of big cities. And here, sometimes people build some water pipe below the infrastructure. So you can imagine you have the pantograph that is connected to the infrastructure of the railway, and you have below the soil some water pipes. Water pipes that can suffer from corrosion effect because of the DC induced current simulated from the pantograph for the railway LRT light road train application. And this is something we can really cover using our tool. And this is something relevant I heard in Canada, so I wanted to mention to you. Now we see that from the experience we matured at Dassault Systems, starting from industries like aerospace and defense, where it was key, you know, to have some antenna placed on the aircraft. Think also about the stealth project, where you have an aircraft that does not want to see by the echo radar. So you are going to design the shape of the aircraft in a proper way to avoid that the echo radar of the enemy is going to look at you. It can be done with a lower observability calculation, and we're talking about radar cross-section. So it's very, very specific application for an industry like aerospace and defense. But all this experience we matured, we use it now for the industrial equipment. And here you have, for example, agriculture or building machines that are used in plants, and you need to simulate them. And I really want to make a deep dive on that application. I'm going to tackle, first of all, the need to design radar. And here it's pretty nice because, of course, a radar, I'm not going to detail too much about the radar architecture, about emitter, receiver, DSP, RF modules, but I'm going to look at more about the antenna itself. Okay, and here you go. Basically, on the nose of your industrial equipment structure, you have some kind of antenna array with a radome, and this is going to do exactly the same as I was mentioning for your car, for the ACC feature. It's some kind of a collision sensor to see if you are going, unfortunately, to meet a wall, for example. So you have to stop your machine. But look at the length in terms of wavelengths. So we have a radar that is at 77 gigahertz, which means something like 2000 lambda. Lambda is a wavelength. So what I do, I use the speed of light to calculate basically the equivalent lambda from the frequency of my radar. And I realized that my structure will be pretty big in terms of wavelengths, 2000 lambda. So I will not be able to simulate it with a simple method. So here we are great because in our solution, we have basically several methods we can use to simulate Maxwell equation. So we have a time domain solver method like a finite integration technique or a transmission line matrix method that will be used to simulate, I would say, a broadband application like ultra wideband antenna. We have method of FEM, finite element method in frequency that we are going to use for IQ structure like microfilters. If you want to simulate an airplane with an antenna on the roof of it, we have method of moments that will provide some surface mesh. But what is nice here is that we are going to couple methods together. And we are going to simulate basically the antenna alone with one of those two methods, so frequency domain or time domain method on the antenna alone. And we are going to see, basically, we're going to register some kind of a near field source, which is basically an equivalent in terms of current in near field of your antenna. And we are going to place the source itself at the nose of my structure. And we are going to solve the full structure with an asymptotic technique, which is the similar one I used for the production plant earlier. Therefore, the method is not only one. I'm using three methods, so I have an hybrid approach, which is a very efficient way to do. And I'm able at this point to fully characterize my antenna and the coupling on the platform. And I want to show, in fact, how we are going to do. So first of all, we are going, in fact, starting from the requirement to design the antenna, okay, to validate it. And we are going to simulate the antenna placed on the structure. And what I want to show is this small chart over here, which is cosine interference, which is a very nice feature, because after you will have been able to simulate the antenna pattern of the antenna mounted on the platform, you will see that maybe you don't have only one antenna. The guy may talk to his wife with a GSM mobile phone, or maybe he can have a walkie-talkie. And all these different kind of antennas are going to interfere together. So what we provide at Dassault System is a tool to calculate, of course, the radiation pattern, but you are going to get automatically some kind of a go or no-go grid cosine interference. Where you are red, it means that you have two antennas that interfere together at a certain frequency. When you are green, that means that you are fine. So the rule of the game will be to bring all the boxes red to green. And this is doable through the software directly to allow then at the end of the day, the manager of the project to validate according to the requirement and validate the KPI of the original project. Now I want to talk more about electromagnetic compatibility. And here what you have several devices inside of your machine. And usually you have some kind of a PCB that is embedded into an enclosure. And so, and this part will be covered by Richard, my colleague, just after me in the demo. So I'm not going to discuss too much about this simulation of DC-DC converter because this is something he will do. But what I want to show is what happens if you put the PCB into the box. The box is going to protect the PCB, of course, from extreme heat because you have this kind of high energy machines and you need to protect and so on. So basically, what we are going to do, we are going to simulate basically the effect of the enclosure. So what we do here, we calculate what we call in electromagnetic compatibility the shield effectiveness. So we simulate the PCB alone, which is the red curve over here between 30 megahertz and 1000 megahertz. And you see the amount of electric field. And we are going basically to simulate the PCB in the box, which is the blue curve. And you see that it's better. You have less radiated field. That means that the box provides some kind of shielding effect to the system, which is good. You have something at 20 dB. Unfortunately, at a certain frequency, a bit below 500 megahertz, you have a resonance. That means that with the box, it's even worse than without the box. So we need clearly to do something. And this is what is done here. So we see that, in fact, the enclosure was not connected. The slots of the enclosure were not screwed together. You see, you have a placement where you can put some screw in it. So what we are going to do, we are going just to put the screw on it to connect very well all the structure together. And this is what you see in green. And you see that the resonance in blue disappears completely. And you are very nice with your result because you confirm the 20 dB of shield effectiveness. Now I want to talk to you about wire harness, I would say cable that you have maybe on your system. This kind of cable are often made with SolidWorks electric solution. And in fact, we are working with the team of SolidWorks Electric to be able to import automatically the cable harness model, both from the schematic and also from the 3D, from SolidWorks. And the idea here is basically to make an electromagnetic compatibility simulation, including the cable harness. So we are going to, at this point, simulate the cable harness, and we are going to model the cross section of the cable that can be quite complex. We are going to basically to take into account the coupling between the cable with the 3D structure. And here we have a unique solution because we have in our method a connection where at each time step, at each delta t, we have an exchange of information between the 3D electromagnetic code, a circuit simulator like SPICE we have into CST Studio, and also the cable tool that basically calculate the crosstalk between cables on a specific cross section using a 2D method. And we couple the three methods together with a unique solution in time domain, which is a co-simulation that provides you a bidirectional link between the cable we are not going to mesh because it makes no sense to mesh cables. We use a cable tool for that and the 3D tool. And at the end of the day, we have a unique solution where we can really even simulate the effect if you have a source antenna on the roof and it brings cable to the it brings signal to the cable and it brings disturbance to the foot of the guy. You see, we have a model we can import and we can put inside the software, and you can see some kind of a BOEM simulation we can do very easily for that person, which is kind of a unique. Voilà, now I will let you watch a very nice video about a robot that is used for oil and gas inspection.
The 3D Experience Works simulation portfolio provides comprehensive all-physics, all-scale simulation solutions for evaluating how your product will behave in real life. With this portfolio, available on the 3D Experience platform on the cloud, you can get the benefits of early virtual testing to assess product performance and quality with confidence. Our design is coming from Square Robot, an innovative company building systems for submerged oil and gas inspections. Such a system is designed for tough jobs in harsh environments. It has to be safe and reliable. Starting from SolidWorks, you can connect to the 3D Experience platform using a unique and integrated workflow that enables you to easily save, manage, and share your design and simulation data in a secure cloud-based environment. But the robot is nothing without its sensors. After all, the main function of the robot is to inspect the integrity of oil and gas tanks, and it needs a multitude of sensors for that purpose. An electromagnetic antenna sensor can be used to detect small imperfections or irregularities in the tank that are difficult to detect with camera or ultrasound sensors. However, the harsh operating environment of the robot also poses challenges for the antenna design. 3D Experience Works simulation portfolio also offers a solution for the electromagnetic simulation for the antenna design, positioning, and performance evaluation once installed on the robot. You can design the standalone antenna and optimize its performance to the desired functional criteria, taking into account the operating environment and the various electromagnetic material properties of the oil or gas in which it needs to function. Or you can collaborate with colleagues who are antenna design experts and can perform that task and then upload the results for your review to the 3D Experience platform. Once the antenna design is ready, It can easily be integrated to the sensor array of the robot, and its installed performance can be verified. Thanks to the guided workflows and intuitive user interface, setting up the meshing and simulation is available to all users, from designers to simulation experts. Here's another example. Being a market leader, IDH tractors are pursuing autonomous alternatives which require the integration of electromagnetic components. With the electromagnetics engineer role, virtual testing can be performed to determine the best antenna placement to optimize performance and reduce the electromagnetic compatibility risk. Engineers can easily track simulation data, analyze key performance indicators, and organize results on dashboards for enterprise-wide collaboration. The simulation portfolio offers a scalable, connected, and powerful solution for all designers and engineers, so they can assess product performance easier and faster than ever. With structural, fluid flow, plastic injection, and electromagnetic simulations, you are empowered to get the right technical insights you need for a new and innovative product development process. With Dassault Systèmes Solutions, you can streamline your design and simulation process today to produce the products of tomorrow.
Right, I hope you like the video. And now we are going to close my part with another example regarding the wireless charging of a smart device you may have at home. So this is a projector that has no cable, so it's fed by battery, and you need to basically to charge the battery with a system of low frequency powerless transfer. So first item you need to do is to basically load your structure into from SolidWorks into the platform. So this is what we are going to see, hopefully. Yeah, here we go. So we are in SolidWorks. You load you save basically your model onto the 3D Experience platform on cloud, and after that you are going to basically to run the electromagnetic engineer role. Yeah, okay, here we go. So here is the launch of the electromagnetic engineer role. Yeah, it's a bit slow. Okay, then you have basically the battery, you have the PCB, you have the cables, and you have the frame, the aluminum frame. So what you are going to do also, you need to charge. So you need to import the docking station and the coil. So you go to the platform and you are going to load on your model, I would say the docking station and the coil that we will need to locate properly into the system that we have. So here you have a yellow-blue dish you see on the screen, which is an anchor point. You can really position at the position you like to place the three parts together at the right position to rebuild, I would say, the full system. Then you are going to create a new project for this wireless charging simulation, okay? Which is not high frequency case, as we said. It's medium frequency in the terms of megahertz. It's just to charge your battery. And so we use basically a coil for that. Right, so here we go. And now we are going to zoom a little bit. Right. Now the ports are placed and to be ready for the simulation. And here you see the electric field near the coil. And in order to match with the frequency for the wireless charging, we are going to use the schematic view of CST Studio to tune at the right frequency. So you see we are going to add some lumped element in order to tune. And you are going to see the result now very briefly on the 3D view. Here you go. And you see, if you zoom, that you are going to match the A4WP wireless charging standard that is the reference for this kind of simulation. So you saw in this example how it's possible to have in one unique simulation, first of all, the smart BIMI, the smart projector, the docking station, the coil, everything positioned at the right place, and be able to tune at the right frequency directly through the software. Yeah, that's all from my side. I will let my colleague Richard to continue with a nice demo.
Hello, everybody. Thank you, Emmanuel, for the nice presentation and also the video. And in the next 20 minutes, I will cover also all the short online demo. Just hold a second. Let me share you my desktop for. So now I'm sharing my desktop. Hopefully you can see it. So I will cover all this the three most important typical PCB analysis. So that will be the signal integrity, the power integrity, and also the EMC analysis. This slide show you also the possibility different kind of analysis can be done also. For example, the RF interference, partial RC, and thermal simulation. But I think in the next 20 minutes I will not be able to cover this topic. But let's see. And well, I will start directly with the first step for the building your simulation. The most important part will be to have a data import into your system or into the simulation environment. So what can be done, or what kind of import we are supporting. And here you can see we have two type of different import file that the import format that we are supporting, the ECAT. So this is the PCB format import. So if you have a different PCB layout tools, then we support all of them. So if not the case, then we are still supporting the ODB++ format. This is the most universal format. It's kind of similar like in a Gerber, but it's more advanced. And here you can import it into our simulation environment. Also for the mechanical import or the 3D import, we support also the CATIA SolidWorks, but in general, we also, the most important also format like the native, the step file or the STL file, this is also supported. So, and before I'm talking to, directly with the slide, maybe I will show you directly with the online demo. So if you open the CSC Studio Suite, first of all, you can see that there are different kind of modules. Here are display, and then you can see that this is the 3D simulation modules where you can simulate the antenna design and also the EMC. So if you click on it, then you can see the high frequency, the cable, and low frequency. And for my part, I will focus first in the power integrated simulation and the signal integrated simulation. That will be the PCB and packages module. So I will click on it. So once this is loaded, the user interface is loaded, then you can directly import the file. So you can go to the EDA import here, or you can easily just, I will take here the file, the ODB plus, you can just easily drag and drop. As soon as it's done, then the program will automatically recognize this is the ODB++ format. And you just press the import button. It takes some time, so even less than 1 minute. And afterwards, the program will open this, what we call a simulation wizard. So this will guide you step by step what can be done or what has to be done in order to launch the simulation. So the most critical part, of course, you can really see here that we have to check, first of all, the stack up. In general, the ODB++ format contains already this stack up information. So if this information available, then you can see here, for example, in this layout, then this information will be automatically recognized and will be imported. You can change all this information. You can change the unit length to millimeter, micrometer, depends on your preference. You can also click on view, where you can see the different stack up here. The information is also display, and you can see what will be the cores and what will be the pre-preg here and the position of the conductor. And of course, if you finish or if you have specified already, you can create a stack up definition file where you can later on reuse it if you have a different PCB layout formats to be imported or the PCB layout version. And afterwards, you go to the next step. we should check the nets. So these nets should be checked because this is related later on if you would like to start the power integrity simulations, because the program needs to recognize which nets belong to the power nets. And for this case, we need to tag several power nets and classify them into the correct net classes. So for instance, here we have a 1.2 volt power supply net or 1.5. In general, the program doesn't recognize it, so it will put everything, or it will classify everything will be in the single-ended. And then of course you can specify them one by one, just double click on it and then you can specify the net classes. Or the easiest way, we have a function we call auto tagging. And in this auto tagging, you can edit the tagging. You can just type 1.1 volt star, 2 volt star, or you can basically add as many tagging as you want. And then of course you can save this again, auto tagging, so it can be later on also reused for the next project. Just press the start and the net will be also tagged automatically. And if I close it, then you can see directly the power net is already automatically tagged. And there is a specific column also here, the differential net. So the program also recognized automatically the signal nets which is belong to the differential. So typically you have an N and P, but if you have a different tagging, then of course you can again extend or you can define the tagging by yourself. And for the signal specification, this can be ignored, or if you would like to specify a certain signal specification net, then for example here I have a CSI, so this is for the camera serial interfaces. You can specify them, and we have here the library different signal specification, and I put it here, I define it as a LVDS, low voltage differential signaling. And this signal specification will be later on used only for the board check functionality. So I will show you briefly the CSD board check functionality, but this will not be used for the simulation. So for the signal integrity and power integrity, this is just for the board check analysis. So once, for example, if you have done all the steps, we just go next step to the PCB check. So the PCB checks will check automatically if you have like a error in the layout definition. For example, you have a net ground overlapping with the net power, for example. The program here will recognize, and then it will show you here the warning which nets are overlapping, and then you can apply the next steps. For example, you correct the nets. So I will go to the next part. This is also the most important part, the component. The component parts are imported as well. So this are defined also in ODB++, and the program automatically recognize. You have the part library and you have the component names. So I think it's pretty clear. So this is the part library. So one library can contain several of components. You can just type the filter 100N and you can see the list of the components which belong to this library and the corresponding value, the model. So the name in 100N. So in this case, we have a 100 nanofarad for sure. This is ideal model. So if you would like to have a different, let's say you would like to include the parasitic of this model, then definitely this is possible. We just press edit. You can choose either the standard model where you specify the RRC. If you have a touchstone file, you can load the touchstone file, or you have a vendor model. In this case, I have several vendor model from Murata, for example. I just press use, and then you can see that this model will be is already directly attached. If you press OK, then in this case, the part library 100 nanofarad will use the vendor model, so that is already attached, and several components belong to this part library will definitely or will be assigned automatically with this vendor model. And then afterwards, if it's already been done, then we go to the next step. We should choose what kind of simulation we will have to do. So these two, there are 4 simulation analysis, but in general, there are 2 analysis. This is the signal integrity analysis, and this is the power integrity analysis. For the signal integrity analysis, there are again 2 types of analysis: the SITD, signal integrity time domain analysis, as it already the name called time domain. So here you can start the analysis for your interconnect interfaces, where you can see later on the waveform. So you can see the overshoot, the undershoot of your signals. You can see the delay, and then afterwards you can wrap this time signal, and then you can see it as a eye diagram. But some of this analysis also has some certain requirement, for example, in the S parameter type. So for example, if I remember correctly, like in the serializer, a deserializer, or in the USB requirement, they have also some specification in this frequency domain. So it's typically in the S parameter, for example, the insertion loss, the return loss, or the coupling, the near end coupling between one net to the other net. And for this analysis, we have also implemented, this is so-called SIFD analysis. And if you would like to study the power distribution network of your PCB, so if you'd like to study how good is the impedance of my power supply net, then this is the power integrated analysis options. So this is PI analysis is for the high frequency analysis, where you get the impedance curve versus the frequency. And for the IR drop analysis, this is the static analysis, which only consider the ohmic losses of your copper. So I will start with this SITD analysis. So for the SITD analysis, what kind of steps that you need to do? This is pretty simple. By the way, this is the layer view. So you can switch on and off several layers to go into the several layers. Of course, you can do the multiple selection, or you can activate different layers. On the right bottom corner, there is some several navigation. If you just keep your mouse there for 1 second, then you can get the information. And we have also the 3D perspective view. If you click on it, then we choose, I just click it and then click on the rotation, then you can also rotate the PCB. You can zoom in, zoom out, you can pan, you can see the several nets here displayed. So I will basically again deactivate this and then going from the top view. And then I will select, for example, the signal layer. And then here, for example, I have several signal interfaces on this signal layer, and also here signal layer as well. And here you can see, for example, if you would like to analyze, I will also activate the top layer. So if you would like to analyze, for example, the communication between the CPU U1 and the memory bank UA, for example, and the steps for analysis the SITD, the first step will be the selecting the component. So in this case, I just double click and the program will automatically move to the component U1 will be automatically highlighted. You just need to double click on it. We need to edit the component. We need to assign. So typically for SITD analysis, we assign the IBIS model. So this is the chip model of this component, but doesn't contain all the parasitic information inside the chip, but it only contains the I/O buffer. So it's containing the response of each of the pin, the rise time, the fall time, behavior. Just quite straightforward. If you have the model, just press apply and the program will automatically recognize. based on this pinning. And then of course, if you can do also repeat also the next part, for example, here the U8 in this case, just press edit the component model. You can assign the model again. And then here again, quite similar, you can see that the model is automatically been assigned. So the last part will be to go directly into the SITD analysis. You can search the net that you would like to analyze it. You can do the multiple selection. We bring it to the right side, and then here you can see the model, the IBIS model already automatically assigned, the nets and also the pin. So we have the source will be from pin number U1, and then this will be the let's say the termination. So the last part will be to define a stimulus. So you need to specify the stimulus. For example, the rectangular pulses. You can specify, or you can even define your own stimulus name. I just pick the simple one, and you can specify it by the frequency. For example, 1066 megahertz. The sequence is either the sequence 1010, high, low, or the random bit signal. And then afterwards, just multiple selection, click on the wire right, and then for the other part, I just basically put it some quiet here, so it just basically a termination. So what we can see here that I assign already the component U1 and U8. These are the nets which I would like to analyze. This is the IBIS model, and this is the sequences stimulus. And then here I just said I would like to have an eye diagram based on the stimulus which I have defined. And then you can press the start simulation. So it will take some time. So that's why I will jump to the other model which I have already pre-calculated. Let me switch shortly and then move the model here. So this is the same model that but I've already pre-calculated. So you can see that we have this oh, okay, maybe I forget to also explain that whenever you open the project, you will always see these two tabs, the PCB and the schematic. This is what already been mentioned from the presentation from my colleague Emmanuel, and this is always tied together. And if you switch to the schematic, then you can see the middle box. This is basically the PCB box. What we the box contain a PCB, and this contain all the parasitic informations from the PCB, and then the outer connection is they are the IBIS models, and these are automatically connected through this task SITD. So once the simulation task is done, you can just go to the navigation tree, going to the SITD. You can analyze the signal. So this is, for example, from the U1 signal, DDR3DQ2, for example, and then we just need to go to the other side, the termination side, and the receiving side, where we can see here, you can see some analysis, some overshoot, and then how the signal looks like at the end. So at the receiving side, so most of the part you can see also, you can analyze the delay between the transmitter side and the receiver side. But if you would like to study this with a bunch of signal, and it might be very difficult because we have many signals. And what is also interesting is to have an eye diagram, and this eye analysis is already calculated automatically from the SITD. So what it does is it just wrap all this time signal into one period the whole time. So it will take one period. It take sorry again, was just mistake. It take one period of the signal, and then it just basically wrapping the signal. And then you can see from this, and this view will be even better. Then you can see directly how the signal looks like. Is it wider enough, and is it the eye width and the eye height is this already meeting your requirement? Because the smaller the eye width and the eye height, then definitely it will be difficult to understand, or it will be difficult difficult to recognize the high and low signal. And you can also study what is the position of this, for example, the crossing point between this signal and this signal, and then you can directly place the measure line. You can measure directly the distance. So this will be the delay. So I just have a slight delay here. So this is typically the SITD simulation results that you are observing. For the SIFD, this is pretty easy also. That basically we just define the source and and also the receiver side, and then when this is done, then you get also all the results in terms of S parameter in this case. And the last part will be the power integrity part, and the power integrity part, maybe I can show you slightly from the presentation here. So we have a power integrity analysis, we have the power distribution network, we have the RLC. So as a simplified power plane, what the DC analysis is done is we analyze the ohmic losses to see how many voltage drop we have from the battery to the load, where for the AC analysis, the power integrity analysis, the parasitic information LSC also take into account. The results, what we receive is the impedance curve versus the frequency. So the impedance, what the load see into the structure, and also you receive the spatial plot. So you receive the impedance plot over your power supply. So this is, for example, like this. And then you can recognize at this certain area, so at this frequency, at this certain area, I have a higher impedance. And that's in this case, I need to place some decoupling capacitor, for example, and then you can analyze it again. You can place a decoupling capacitor, so you can really see how the impedance curve will looks like. And then in general, you would like to have a smooth impedance curve or impedance plot. And for the IR drop, it's also the similar, but in this case, you get the impedance, you get the voltage drop, because this is more meaningful results. And again, you can see also the voltage drop from one part to the other part. And then afterwards, you can see whether this drop at a certain area is okay, or if it's not okay, then you can again adjust the layer, so the layout width at this certain area, or remove some holes. So these are the power integrity analysis. Moving to the EMC analysis. So in this case, I will shortly cover the battery. So if you see here the batteries, and typically the battery will be the switching mode power supply. So we have a buck converter of the boost converter in this case. And in this case, you have typically the conducted emissions or the radiated emission, because we know most of the cases that the SMPS is one of the major noise. EMC noise contribution. So for the conducted emissions, this is the noise coupled to the power line. So this is typically your SMPS, which is connected directly to the DC source. Also the same thing, you can also perform the radiated emissions, where in this case, either your DUT radiating, or you have a two wire. So you typically you have a power positive and negative, and this also radiated. And you place the EMI receiver. So in this case, we place probes. Before I explain, so this is you define probes surrounding the calculation domain, and you receive later on the results. So the E field strength at the probes at a certain area. So I will move back again. So the workflow is pretty similar, but in this case, we move to the 3D EM simulation. First of all, you need to have the model geometry. In this case, we have the PCB. If you have a mechanical housing, you can also combine the PCB layout and also with the mechanical. In this case, we will launch the 3D EM simulation because for the EMC we have a field radiation. That means we need to consider everything in the 3D modeling. And then also we go to the circuit simulation, a circuit setup, and we set up the circuit, we do the simulation, and then we analyze the results. So for this case, I will take an easy example. I will close this. So we go to the 3D simulations, or what is this, the interesting also what we have is we have a project template where all the setting has been set up according to the certain application. So for example, for the EMC, you can pick a radiated emission, conducted emission. And once the setting has been done, then it will be stored. So for in this case, I have already EMC conducted emission template. I just selected on it. And the 3D EM simulation environment will be automatically open. Just drag and drop. And then here we are going into the EDA import user interface where all the components are recognized. So I'm not, for example, you can also deactivate the whole import component, or you can activate it. Typically we deactivate this one because we'd like to replace all this component connected to the SMPS with the SPICE model. So what we need is we select a couple of components. For example, here C1, C4, for example. I just pick some arbitrary, and then you click to the ports, and then you can just move it to the right side, and then you can really see that all the ports. So this is, I have already prepared several components which are related to the simulation for the SMPS. So this is the buck converter. And afterwards, if you finish, then you just press finish import. Okay. And then the model is just imported. And as you can see, this is everything is in 3D. So the layer thickness, the PCB, the vias, everything imported. And this red cone representing the position of the component in your structure. So these are, for example, the capacitor, SMD, and this is the transistor, the diode, and so on. And similarly to the PCB Studio, in this 3D simulation, you always have also two tabs directly tied, 3D and the schematic. So the 3D will generate, will calculate the parasitic information of this layout, and then you move to the schematic, and here you need to connect the component. So the labeling of the component is already taken over, so it's just easier for the user to directly connect it with a certain component. So C6 will is for the capacitor, and then for the diode. So I will switch back here to the pre-calculated model. So in this case, for example, I have already done all the schematic. So this is what you can see. I don't have a transistor model because this is the point where I don't have the transistor model. So if you don't have a transistor model, you can still use the switching block where you define the transition width of this, when should be turned on and turned off. So the on resistor, off resistors, and then afterwards we define the periodic rectangular pulse signal in this case. After you run the simulation, you can go back to the 3D simulation. You can later on analyze all the fields. So I have defined the probe. So I have a probe above this switching nodes, but you can also analyze the signals, the surface current. You can see I have a bunch of labeling here. So what is the purpose of this? So the advantage is using this simulation with this Microwave Studio is the unique feature what we have is you can define several subtasks inside one tree here, one navigation tree. So the benefit of this subtask is then you can define, you can study you can make it like a what if scenario study. For example, what happen if I try to activate the input filter. I would like to see what kind of input feature I need. And you can specify this subtask. And then, for example, a next subtask is you can say, okay, I would like to have a ferrite bit also implemented, and you would like to see what is the impact of this result. So the first task will be your reference, and then you can define several subtasks, and you can compare the results later on with the reference. You can also define subtasks, for example, a snubber. What is the results afterward if I define a snubber? Or you can also define what if I have a different transistor used. For example, I use a P MOSFET, or I am using an N MOSFET, and so on. And also you can also define another subtask where a 3D model also coupled here. So again, it opened the 3D model, and here, for example, you can do the layout modification directly here inside the Macro Studio, where you can say, okay, I would like to reduce the switching loop, for example, in this case. And then, so here you don't need to go back again to the layout and import again with the ODB, but you can directly also modify, and you can directly see the results, and you can compare. So these are the results folder where you can put as many results folder as you want. You can just copy paste. You can switch to the dB, microvolt per meter. You can afterwards plot the frequency, the scaling in the log, and then you can see what is the impact directly if this is my original structure, for example, and this is the once I define, for example, a snubber at the diode, what kind of improvement I can see. For example, in this case, I have seen some improvement. And then you can also compare with the different, this is the spectrum. You can also compare the time domain spectrum, not the time domain spectrum, but the time domain. So where you can see with the snubber, I have the ringing, and with the snubber, I can reduce the ringing. You can move, and then you can also activate the measurement line. You can measure this. And finally, of course, you can move back, and then you can try to also visualize the surface current. So this will take some time because it will to calculate the whole 3D model, and it will later on plot the 3D plot. So the calculation will take some time because I have a lot of, but I have already prepared in the presentation. So for example, you can see how the surface current distribution looks like at the 488 kilohertz at the switching frequency, where you can see how is the current look like when the switch node is closed, when the switch is open, and of course the most critical part is the high frequency loop here during the transition. And so the conclusion of this is the unique feature what we have is we have a 3D simulation. From the 3D we go to the circuit, and then again afterwards we go back again. So this is one of the unique features, and I will skip this because time is running out now. And then at the end, just to show you some benefit with a simulation. If you have a simulation as an integration part of your development process, where you can have several development loops using the virtual prototyping, where you can directly modify and see the improvement of the layout without necessarily having the first prototype. And surely if you have if you're going into the design validation where you have a prototype, your first prototype, you can still do the modification in the simulation where you can see if there is a benefit or not. And then afterwards you move to the last parts where the product validation, where in this case the design is already fixed. So that's it from my side. Thank you. And now we can go to the Q&A.
Thank you very much, Richard. This is Roman Duplac speaking. So we are out of time already for the question and answer period. So instead, what we will do is, instead of having a live question and answer period, I encourage everyone to send in, to email in or call. Ideally, email your questions, and then we will be able to respond to them. So any questions you have, please send the email out.
Perfect. Thank you, Raman. And thank you, Emmanuel and Richard. That was a great presentation. So like what Roman said, if any questions do arise here, you can send him an email or reply to the webinar email and we'll be in touch. Once again, thank you so much for a great presentation and thank you all for joining us here. We hope to see you again soon. Thank you.
Thank you for joining.
Thank you.
Bye-bye.
Bye-bye.
Thank you everyone for joining. Bye-bye.